Let's get started. Let's see. So logistics. Problem set number 4, as you know, is due tomorrow, not at the normal time, but we're giving you a few extra hours. That'll be due at 4 p.m. In the normal place, basement of Campbell Hall. Problem set number 5 will be due the following Wednesday, and we'll assign that either tonight. Well, actually, we'll probably assign it more like tomorrow on B-Space. My office hours are, as usual, 3 p.m. to 4 p.m. today, Campbell 5 to 7. And a colloquium, even though we keep calling these things colloquia, they're supposed to be sort of big luminaries giving these talks, and they are. We usually have them only once a week, but we've been having them pretty much 2 or 3 times a week this month because we have all these special visitors coming because our department is hiring 2 faculty members. So all these people are potential new faculty members, and they may impact your academic career. So you may be interested in seeing what they have to say. Galaxy evolution, Shelley Wright is currently a postdoc in our department, and she works with adaptive optics imaging. Did you talk about adaptive optics in 7A? So you know all about that. She's sort of at the forefront of instrumentation, thinking about adaptive optics, both using the Keck telescopes and then new very large telescopes, 30-meter telescopes and beyond, over the next decade. Questions on logistics? Yes?
Problem set 5 doesn't do at 11 again?
Yeah, we're going to go back to 11. We assigned problem set 4 a little bit late, so I felt a little bit bad, so I gave you a little bit more time. If we get it done on time, then 11 a.m. seems okay. Is there a big clamor to have it due much later?
It's nicer, actually.
You don't have to wake up this early.
Oh, it's waking. You have to wake up to do this? I don't know. So neither of the GSIs are here, but what do you want? What do you want? 2?
Yep.
All right. 2 from now on. Done. I just have that kind of power. That feels kind of good, actually. I can give hard midterms. Yes. All right.
I had a question relating to that stuff.
Okay, I'll get to that stuff. All right. So any questions about logistics? Okay. So last time, we talked a lot about celestial coordinates and how we localize objects in the sky. We also mentioned parallax, which you've seen before, but I wanted to go over it once again. We're going to get back into parallax, in particular something called statistical parallax, next week. But in terms of localizing objects on the sky that are fixed with the celestial heavens as they rotate or appear to rotate around, we generally use equatorial coordinates as astronomers. It's fixed to the Earth's spin. And remember, the ecliptic is fixed and actually set up by the Earth's motion around the sun. The 2 main angles are right ascension, symbolized with an alpha, declination, symbolized with a delta. And given any of these 2 coordinates, and given basically the definition of where alpha starts, where the 0 angle is, declination is quite easy because it's basically the declination off of the equator. But given that definition, we can basically localize any object on the sky. Now, of course, we said the object could be moving, have an apparent proper motion, because it's actually got some space motion relative to how the sun is moving in the Milky Way, and that could manifest itself as motion over time. Because of parallax, it appears to wobble back and forth, and the combination that basically makes stars all look like this. One of the things I failed to mention explicitly was that we usually talk about these coordinates in a certain year or a certain epoch. We say this was the position of this object in 2000 coordinates or 1950 coordinates, or what's coming up is 2050. And the reason is precession. You can imagine, of course, because the Earth's spin is precessing around, that the location of even a star or even a quasar, which is very far away and doesn't appear to show any proper motion, is fixed with respect to the celestial heavens, but because the Earth is moving around, the apparent location in these 2 angles is actually going to wind up changing. This is kind of annoying, but what we talk about is usually something called the J2000 coordinate system. It sounds like a computer, but it's a coordinate system, as opposed to the B1950. You don't have to know all these things. But the point is that if I gave you the location of, say, a quasar in these coordinates, in 2000 units, it would be in a slightly different set of angles in 2050 or even this year. So you have to worry about these precession. The precession terms can be quite big, but because we know how the Earth's precession is actually progressing around, we can make these coordinate changes at any time. It's pretty easy. Okay, did you have a question about this or magnitudes? Okay, so magnitudes, just to summarize, little m1 minus little m2. Little m refers to the apparent magnitude. So that's as we view it. It's related to the flux. And it's related to flux in this way. We think of magnitudes as basically a difference between some fiducial brightness of some fiducial source minus 2.5 times the log base 10 of the flux of the first source divided by the flux of the second source. Little m minus big M, where big M is the absolute magnitude, is 5 times the log base 10 of the distance divided by 10 parsecs. This is just a recasting of the 1 over r squared law. Just to give some context, we said all this before, but just to summarize, that little m, usually when we talk about M2, for many coordinate systems is the star of the Vega star, which has, by definition, a 0 magnitude. So that means if I know how bright something is relative to Vega, then I can figure out what its apparent magnitude is. The absolute magnitude of the sun, 4.74. That's as bright as the sun would appear if you put it at 10 parsecs. And little m of the sun, because it's much closer than 10 parsecs, is something like minus 27th magnitude. Okay, Pauline.
Yeah, so if we're trying to find just m and we're comparing it to m Vega, what flux should we use for Vega?
Well, remember that Vega has a very peculiar spectrum, right? It's an A star. And A stars are very blue. But they also have sort of spectral features and lots of dips. The answer is you'll have to get, if you really want to do this, and if I gave you the flux of some star in some bandpass, say in the visual band or in the R band or any other bandpass, if I gave it to you in MKS units, you'd have to know what Vega is in MKS units as well. So it's not a trivial exercise to do that. It's usually easier to take it like something relative to the sun. So if you have the apparent magnitude of the sun or the absolute magnitude of the sun has sort of colors that are similar to many more stars. If you've got a weird spectrum, you have to take into account that spectrum. Remember, I showed you that figure where I had a blue star and a red star, and they had different spectra going through the different filter systems. So even though they had the same flux at R band, they actually had different fluxes in those other filters. Did you have a specific question about it?
No, because I was just thinking if we're just trying to find one m instead of a difference in m.
So that's really the trick, is that when you talk about magnitudes, it's just so much easier to talk about them in terms of differences relative to something they just define the 0 point. That's because of the strangeness of the spectrum of Vega. That's actually why people aren't very happy with using Vega. And I mentioned last time that there was this other alternative called the AB magnitude system. And for that, it's just minus 2.5 log base 10, the integral of the flux of the object, times this response function of the filter integrated from 0 to infinity over all frequencies, minus 48.60. This is just a number so that Vega has about 0 magnitude in the V band, the visual band. You don't have to know all this stuff. So if I just gave you physical units, right, or I gave you a spectrum right here, so here's the spectrum of your interesting object as a function of frequency, then I know what my response function is here in appropriate units, and you're more or less just doing an integral inside here. And once you have that integral, if you've done it in the appropriate units, you just subtract off that number, and magically you wind up getting an apparent magnitude. So that's how you sort of get away from having to do it differentially. In general, the magnitude is something that we could subscript with a lambda, and this is going to be minus 2.5 times the log base 10 of the flux f lambda plus some constant. So this is either defined because I just give it to you, or it's defined by some magnitude of a star that you define as the sort of characteristic star of the magnitude system. And likewise, minus 2.5 log base 10 f nu plus some constant, which will be a different constant, nu. And what I said last time, just put down in words, is that we can go back and forth between what many astronomers like to use as this f nu. What was the units of f nu? Without looking back in your notes, it's a flux. So what is a flux in MKS units? Joules per second per meter squared, and we subscript it with a nu, so that's a hertz per hertz. And somebody noted yesterday or the last time that hertz is 1/2, so you could just call this joules per meter squared, but this is sort of convenient to look at it this way. And likewise, f lambda is units of joules per second meter squared, some usually per angstrom. And this is units of length, so it's really joules per second meter cubed. So they're actually different units, but they're both used to define this flux. Nu times f nu is equal to lambda times f lambda. And since nu times lambda is equal to c, we can go back and forth between f nu and f lambda. Okay? So basically, there's just sort of an apparent slope change as you would wind up plotting this. Yes?
Is it typical to use angstroms for x meters? Sorry, I always thought that it would be more like it was typical to use meters to calculate like the meters for that.
No, it's typical. I mean, you can do it in any unit you want as long as you're sort of paying attention to how everything scales. But it's typical to do it in angstroms or microns. But you almost always see this in units of angstroms. Overall, that's just going to be sort of an overall scaling on what your y-axis is, right? But in terms of seeing the overall shape of things, that doesn't really matter what units you use here. Okay. So I think it should be clear by now that we take filtered images of the sky because it's just sort of easy to do that. You have a detector, you put some colored filter in there which has some response function. And then it allows us to get a sense, if I have multiple images in multiple different filters, of the colors of stars. What we're really trying to get at, and the reason why we spend a lot of time thinking about this, is because what we're really trying to get at is the Hertzsprung-Russell diagram of the stellar population. And those that haven't seen Hertzsprung-Russell diagram, please review that in Carroll and Osley. This is usually called the HR diagram for short because it's difficult to say Hertzsprung-Russell very fast. Hertzsprung-Russell is nothing more than just a plot of the apparent temperature of a star versus its luminosity. The apparent temperature is something that we could more or less get if we had a very nice spectrum of a given star, right? You just fit a black body, and even though there's some absorption lines and things, you wind up getting an overall sense of what that temperature is. Redder is cooler, bluer is hotter. So it's actually sort of plotted in a strange way with temperature increasing to the left over here. What you see here are the different classifications which have historical meaning. Don't really matter that you actually know these. Going from O stars, which are the hottest, down to M stars. And in fact, this sequence extends even further after this was made. There's L and T and maybe even Y dwarfs. What's that? You're doing your mnemonics? He did?
Yeah.
With a Y in it?
No, not with L and T.
Okay. There's a Monica Lewinsky with M and L, actually. You can Google that. I won't tell you what it is. So the other important unit, of course, is luminosity. This is not something that we have access to if we don't have the distance to the source, right? But unfortunately, this didn't come out very well. Here's the luminosity in solar units. The sun is right here, so it's about a G star. And what you notice, of course, very obviously, is the main sequence. What you also see is where the giants and the supergiants live. And you also see that the white dwarfs fall well below the main sequence, where they're actually very hot, but their luminosity is very low. If you think about the Stefan Boltzmann law, luminosity going like the emitting surface, so that's going to be r squared t to the fourth, you can draw lines of constant radius here. And this is what's done. It's very hard to see this. You'll see it better when I post these notes online. This is a line of constant radius. This is a radius of about the radius of Earth, something like 6,000 kilometers. This is obviously the radius of the sun. And then it goes up by, I think, a factor of 10. So what you notice is that white dwarfs have similar radii, and the radii of stars varies by something like a factor of 100 on the main sequence, but the supergiants can be much larger. So what we're trying to do is we're trying to take more or less an easy way of getting this spectrum, an easy way of getting this temperature, and then if we have a sense of distance, then we can wind up producing our sense of luminosity. Clearly, if I take a picture of a group of stars that are all at the same distance, and I get a bunch of different colors, then I can kind of use the apparent magnitude of all the objects, if I know that they're all at the same distance, as a proxy for that luminosity. What does it mean here when we do that? Well, instead of getting a spectrum of a bunch of stars, this is going from O stars or B stars all the way down to G stars. And you notice the tilt of the spectrum here. This is relative flux, but that could be F lambda or F nu. You notice as I go down in wavelength, so I go up in frequency, the bluer stars are indeed brighter in flux. And as I go farther and farther down, I wind up seeing that there's all these different features, but overall the color becomes redder. That is more flux in the red bands over here. Typically what you would do is take a set of images in the U band, the B band, and the V band filter system. You would make a color plot. And from that, you could infer some measure of temperature, and you could, if everything's at the same distance, make a sort of inference of the luminosity. So this is this response function for a given filter system. Does anyone have any questions about what I'm showing you? Okay. So what we actually get is not an HR diagram per se, but what we can make is a plot of some sense of color. And those of you who have been working on your problem set have already seen this nomenclature before. It's a B. A B is a subscripted way of saying little mb. V, of course, is a subscripted way of saying little mv, just sort of shorthand for doing that. And what you see is that we have a main sequence here, but it's sort of all flipped around. The redder stars are here, so the B minus V color is large. So let's think about that for a second. What is B minus V of Vega? It's a blue star. No, how do I define Vega? 0, right? B minus V is 0, B is 0, V is 0, everything's 0 with Vega. Okay, so this is where Vega should be, somewhere up in here. If I go to larger differences of these magnitudes, what is that saying? It's saying that the B magnitude is larger than the V magnitude. Larger means less flux. So as I look at the B band versus the V band, if I go back, B band versus the V band, B is bluer than the V band. So if I have a larger quantity, it means it's bluer or redder, without looking at the color scheme. That sort of gives it away. Yeah, so if I have a large B minus V, I'm going redder and redder and redder. So indeed, this is where all the M dwarfs are and the red dwarfs. Up here, this is sort of inverted, right, because I have magnitude in the V band, and the higher up I go, the brighter the object is, right? So this is the opposite of luminosity. If I turn this around, then I would wind up getting more or less what I had before. And you can see on luminosity over here, you notice that luminosity goes down this way. Also, what you see is the effective temperature on the top. So as I go to larger B minus V, I become more red, down to the sort of 4,000 Kelvin. And you also notice that for this grouping of stars, you wind up losing a large part of the main sequence. It looks like all the stars have sort of what's called turned off the main sequence. And it turns out that if you look at the location of what's called the turnoff, this turnoff place in magnitude, you wind up getting a proxy for the age of that system. So I believe this is a globular cluster, and so we can just take basically an image of this cluster of stars whose distances are all probably about the same. What are these objects up here? Yep. So without having to take spectra, which is quite expensive in a sense of using telescope time, of all of these stars, right? There's probably close to 100,000 of them in this plot here. You can just basically just take a snapshot image in 3 colors and plot this up. In fact, this is only done in 2 colors. Any questions? Yeah.
If Vega is 0 and all the bands, why do we take blue star?
It just happens to be a blue star. So this was sort of a bad choice, if you want, historically, of a star that defines the whole magnitude system. If you look at the spectrum of Vega, I showed it last time. I think it's also in Caranoculi. If you want, I can show it again. But basically, relative to most of the other stars, most stars are sort of faint red stars. There's only a few in an absolute number sense of the very blue, very hot, very luminous stars. Vega just happens to be one of them. So it's actually a much bluer star than where most of the stars are. So you can still use it as a fiducial, but nominally you'd want to use a fiducial which is a lot like the others. Yes?
What does fiducial mean?
Someone pull out their dictionary, but you guys ask me these crazy questions. Fiducial. Yeah, I'm using crazy words, but it's an English word. Fiducial is sort of the prototype or the nominal.
It's like a standard.
It's a standard. You knew the answer, you just asked me. No, it's certainly not astro jargon. That's English jargon. Okay, so if I'm doing any astro jargon, you're right to call me on it. And you're right to call me on it. What's that? V is visual. So there's actually another band called R, which is like red, and there's another band called I, which is like infrared. But these are just historical names, basically. But blue and visual are kind of the way you would remember these. And U is ultraviolet, sort of, although they're not really ultraviolet. Okay. So any questions about that? So this is why we take images of stars, as we'll wind up seeing when we take images of galaxies. We use some of the same sorts of diagrams to help us locate different types of galaxies in this space. Galaxies are just a grouping of stars. So if I have a very old galaxy, most of the blue stars have left the main sequence, right? Because the time that stars spend on the main sequence goes very strongly inversely proportional to their initial birth mass. So if they're basically born very big, they turn off the main sequence very quickly. Old galaxies are very red. Young galaxies, if you want to think about it that way, or at least galaxies that are forming stars very copiously, I should find that, they tend to be very blue. Because it turns out that the blue stars outshine the red stars, even though there's many more red stars. Anyway, so we'll come back and we'll keep on using magnitudes, first of all, today in the context of dust. But when we start talking about galaxies and galaxy properties, the reason why we had to actually think and work on magnitudes now is because we actually just take images of the sky. We take spectra of those galaxies as well. but it's just so much easier to take images. And to understand where those galaxies are with respect to the other galaxies and see how galaxy properties correlate with each other, you have to have a pretty good intuitive understanding of magnitudes. Okay? I know you've seen it before, but I'm going to keep beating it into you. All right. So now we're really going to start moving on to understanding constituents of the Milky Way. In particular, today we'll talk about dust, and we'll talk about the interstellar medium. We'll talk about the interstellar medium really in terms of its constituents, not so much what are called the phases of the interstellar medium when we talk about different blobs that have different masses and densities and temperatures, but really the particles within the interstellar medium. We want to understand where these particles came from. A lot of it turns out to be fairly primordial, so it's basically made in the Big Bang. A lot of the trace elements were made in stars. And you've probably seen this before, but it's sort of worth showing again, the idea of this sort of recycling of material. And in particular, during the Big Bang, as we'll see in the last third of the class, we wind up making basically all the hydrogen and helium in the universe, and a little bit of trace elements like beryllium and lithium. But beyond that, any heavier elements, which we sometimes just call metals, so anything basically heavier than helium is, for an astronomer, called a metal, sort of strange, is made in stars. So the first stars were formed probably about something like 300 million years after the Big Bang, thereabouts. We don't know exactly how those first stars formed, but they did. They wound up undergoing fusion processes. They wound up blowing up as supernovae, and both of those processes wind up creating heavier elements. Those elements wound up making their way into the interstellar medium of the protogalaxies. And that interstellar medium, if it had the right conditions, in particular satisfying the Jeans criterion, which you saw last time, will wind up forming stars. But those stars now don't have a primordial composition of elements. So you have the star formation cycle. You wind up making stars. Those stars themselves wind up blowing up and expelling material into the interstellar medium. You wind up enriching the interstellar medium even further. So there's this sort of forward progress of enrichment, of really just nuclear waste of stars that goes into making up the next generation of stars. And that cyclical process is one that you've seen in 7a. We'll touch on it somewhat over the next couple of lectures, but it's something to just bear in mind that one of the reasons why we think about the interstellar medium in sort of a smaller scale sense is because we have to understand the formation of stars. That's something that you've already thought about in 7a, but as we move on from that process, we now think about the interstellar medium as a constituent of the Milky Way, as a constituent of other galaxies. And on large scales, these are things that we can actually observe and understand the detailed chemistry of these clouds and understand the detailed temperatures and temperature structure of clouds, et cetera. Okay, so any questions about that? Life cycle of stars, pollution. Let me now just sort of tell you what we know about the interstellar medium in a broad brush stroke, and then we'll talk about some of the details. The interstellar medium, ISM, is really the stuff that pervades the volume in between stars, interstellar, right? If you want to think about the Earth as being part of the interstellar medium, that's okay, right? Because technically we're between stars. But the way to think about it is that any of the sort of gravitationally bound planetary systems, or you maybe even get rings around newly forming stars of debris that's forming in a disk, that stuff isn't really considered interstellar medium. It's the stuff that isn't gravitationally bound to stars. It's all that other stuff. So we want to know what it is and what accounts for its properties. one of the things that should be very clear is that the space between stars is very vast, and it's also almost a pure vacuum. In terms of density, it's convenient to talk about density in terms of particles per unit volume. And here the average density, call it n bar, of the interstellar medium is something like 1 particle per cubic centimeter. Note, this isn't per cubic meter, but it's convenient to think of this as 1 particle per cubic centimeter. And it can go up to something like 10 to the 6 or maybe even 10 to the 7 particles per cubic centimeter. These very high density regimes, this is actually where we wind up seeing the sites of star formation. I think on 7A you had a homework problem where you thought about molecular clouds and star formation within molecular clouds. We'll see more of this later on, but this is sort of the densities of molecular clouds. For comparison, on Earth, the best vacuum that we can wind up creating, does anyone have any idea what that is in these units? Go with 100. Anyone else? This is like Price is Right. Yes, you win, actually. It's about 1 trillion. That's the best vacuum that we can produce in a laboratory. And then air, 10 to the 19 particles per cubic centimeter. So vastly different kind of space than when we think about and talk about even on Earth. These, unfortunately, we can't reproduce the conditions of the interstellar medium on Earth. So the only laboratory to study the way that particles behave in these very low density regimes, even this very high density is not nearly as high as what we can produce on Earth. The only way to do this is basically in situ. I'm going to start using lots of big words. In situ, is that all right? In place. So we have to actually study the interstellar medium and understand the detailed chemistry of the interstellar medium using the observations of the interstellar medium itself. Constituents of the ISM, 99% of it by mass is hydrogen and helium.
That's not how you spell constituents.
1% are the trace elements. Carbon, oxygen, nitrogen, neon, etc. And we also wind up getting molecules. In particular, we'll see later on CO, carbon monoxide. There's water. There's many different molecules that we've now observed in space. And dust. Dust, the way to think about dust is that they're really, I'll do it on another board here. Dust are really just grains of large molecules. Is that me? And the primary elements are silicon and carbon. These are sometimes called silicates, and these are carbonates. Carbonates, maybe an I don't know. Typical sizes that you wind up seeing of dust grain, the sort of number to remember is 10 to the minus 6 meters. This is a micron. Sometimes symbolized with a mu m. But it obviously takes on a range of distributions from something like 50 to 2,000 angstroms. So these are fairly large dust grains. 2,000 angstroms is 2 microns. This is a typical size, yes. So it's like a typical radius. I'll show you some pictures of that now. Or should I move this over? Almost. Show you some pictures of some dust grains. We've actually launched satellites, not me personally, but humanity has launched satellites to actually capture dust grains within the solar system and bring them back and then study them actually in the laboratory to understand their composition. It's hard to think of this. This is a very large dust grain, several microns across. And this is seen through I think, electron tunneling microscope. It's very difficult, obviously, to construct these things in the computer, to think about, well, if I take a silicon atom and a carbon atom and an oxygen and a hydrogen and I put them together in the presence of magnetic fields and ultraviolet radiation from nearby stars, what happens? So we don't really have a great sense in the laboratory of what these things should look like or what their composition even should be. But this is one of the ones that I think was returned in the Stardust mission. It allows us to study exactly what that composition actually is. There are 2 things really to know about dust and how they manifest themselves. There's some more subtle things, but the big things are that they create extinction, so they block light, they diminish the incoming light from us that would otherwise be detected by us, and they redden light. This can be seen in a true color image of a portion of the Milky Way. These are the so-called dust lanes that are not created because we have no stars along this sort of black line here, but because there's actually quite a large number of stars, but the starlight itself is quite affected by dust. A large amount of it is blocked, so we can't actually observe it. That's what it means by extinction, overall flux going down. I'll talk more about this in a little bit. Reddening is another effect of dust, depending on the exact size and distribution of dust. Turns out the dust that we have in the Milky Way and probably in other galaxies is all about the same and all about the same size distribution to give us this reddening effect. And that is that light of longer wavelengths preferentially makes it through dust grains. Light of bluer wavelengths is either used to heat up the dust grain, so it's actually blocked, or it's reflected off of these dust grains, and it's reflected away from our line of sight. Yes?
Why is it that, what's different about the dust that doesn't like emit or absorb like hydrogen doesn't? It only right? Like it would typically emit in the infrared just from photons?
Yeah, it absorbs and it emits. It's just acting like any other particle.
Is it from molecular, like atomic transitions?
No, so dust generally emits thermally.
Yeah.
The light that impinges upon the dust grains, sorry, I'm going to catch myself every time I use a big word. Light that impinges upon the dust grain is absorbed, and it can actually do a couple things. One is if the light is energetic enough and it's absorbed by the dust grain and with a certain chemical composition, the dust grain itself can sort of get ripped apart, right? So if you throw a lot of ultraviolet photons at a sort of screen of dust grains, many of those dust grains will actually just obliterate. In fact, the ones that wind up surviving are the ones that are actually larger, if you can imagine. So that's how you would change the overall distribution of sizes of dust grains. If it doesn't obliterate, you're basically capturing h nu of the photon. So you're getting some energy, you're increasing that. That energy can be used in a couple of ways. One is you could somehow wind up increasing the rate of rotation of this, although you have to also preserve angular momentum of the whole system. But more likely, you would just basically wind up heating this up to a certain temperature. Typical temperatures of dust is something like 20 to 100 Kelvin, which doesn't sound like a lot, and it's not. But it radiates, because there's so much dust, it radiates very efficiently as a thermal radiator, and we can actually see dust emitting thermally in basically all galaxies and within the Milky Way.
That's what I mean to ask is like what's different about like the silicates and carbonates that make up dust that it doesn't have like atomic transitions. It only emits and absorbs from it only emits thermal.
Well, so there are some special absorption bands, as they're called. They're not nearly as sharp as atomic transitions, because atomic transitions are, relative energy levels, changing from one energy state to another energy state, and those are sort of quantum mechanically very tiny in the difference of the energies. So you wind up getting these very narrow band absorptions from molecules, which are quite easily happy to receive photons and absorb photons at a variety of different wavelengths. We'll see more of that later. Or even individual atoms, like the hydrogen atom, right? Is very happy to absorb photons of a certain energy and emit them at a certain energy. These molecules are quite complex, and because of their complexity, they wind up having sort of a smearing out of all of these different effects, right? So there is no sort of sharp transition. And in fact, if you were going to throw some light at this molecule, we'll see this basically right now, depending exactly on the angle that it came in at, exactly what the wavelength of light is, it's either going to get absorbed, reflected, or absorbed or reflected, that's about it, or pass right through. This should become more clear over the next 10, 15 minutes. Oh, this is like impossible to see. I have to turn out all the lights. Can you see that? That's actually a galaxy taken at infrared wavelength. So 3 colors, 3 band passes. This is a galaxy which is edge-on, and you can see a couple of features. It's actually much nicer on my screen. You can see a couple of features of this. This is a galaxy edge-on, so this would be as if you're in the Milky Way, but way out of the disk looking at it. You can see these dust lanes in here. This is an infrared image of a supernova that happened at the center of this galaxy, which wasn't detected at optical wave bands because there's so much dust. And the galaxy is extinguished like this, so there's so much dust in between us and the line of sight of that supernova. It wasn't discovered optically like most supernovae are, but it was discovered at radio wave bands. And we took an image of this with a telescope that I operate in Arizona. At infrared wavebands, we were able to actually see that supernova. But in addition, you wind up seeing this very nice, clear indication of these very strong dust lanes, even at infrared wavebands. So this isn't really a visible phenomenon per se. This happens basically at all wavebands. Okay, so just to help us visualize these two large effects of dust. You can draw a little cartoon of some light impinging upon, heading through, interacting with a dust cloud. So we're going to be an observer looking through this dust cloud, and here's going to be a light source. This is on its way to our eye, right? And so we would, if that dust cloud wasn't there, see the spectrum of that source be whatever the spectrum is natively, obviously diminished by the 1/r squared law. But this dust cloud does 2 things. One is that it passes red light preferentially, and it winds up scattering blue light. This whole process is called reddening. And we think of reddening as sort of the transmissive process. But there's also, in some sense, if you're not looking directly at the light source, but you're looking off angle from the light source, it's actually got sort of a bluing effect, right? But we think of dust as a reddening system. The other thing is the overall light, even though it passes through, will be diminished. So this is what's referred to as extinction. So dust makes stars redder and fainter. And we can see how that might manifest itself in a magnitude sense. The apparent magnitude is what we actually observe at some fixed wavelength. This is the absolute magnitude of the source at that wavelength, times 5 log 10 d divided by 10 parsecs. This is the distance modulus. This is what you've seen already. Now we add another term, a lambda. This is called the extinction term. And it's always positive. You can see the immediate effect of that on magnitudes. If A is always positive at all wavelengths, the magnitude is going to be larger than it ought to be, which is just saying that it's fainter than it ought to be if the dust wasn't there. If we think about this in terms of flux, in F lambda extinguished or extincted, that is what we observe, is just going to be related to an optical depth as a function of wavelength times the flux as it would have been if it was unextinguished. Tau lambda is a dimensionless quantity, which is the optical depth at wavelength lambda. If we now want to solve for what this A term is in terms of m lambda of the extinguished minus m lambda of the unextinguished, that's basically the definition of A lambda. This is equal to minus 2.5 times the log base 10 of e to the minus tau lambda. Obviously, the distance modulus drops out. This winds up dropping out. And so because we're just thinking about magnitudes and flux interchangeably by minus 2.5 log base 10 of flux 1 divided by flux 2, you can wind up showing that this is what A lambda has to be. And if you multiply this out, you're basically going to get a minus tau lambda times minus 2.5 times the log base 10 of the number e. It's kind of weird. And this is just 1.0857 tau lambda. So this is actually one of the convenient things that you get from using magnitudes instead of fluxes, is that as you increase the optical depth, even though the flux is going down exponentially, the magnitudes are just changing linearly. So if I increase my optical depth by a factor of 2, I increase my extinction by a factor of 2. Yeah. Oh, sorry, A lambda, excuse me. So extinction proportional to the optical depth. What is the optical depth? What is the optical depth? How do we think about the optical depth?
Percentage of light that gets decreased over a certain amount there.
Yeah, that's sort of here, right? We think about an incoming beam and we think about an outcoming beam, and we just sort of compare the two, and they're going to be different by this quantity. But why do we have optical depth? What is it that's actually happening to the light? It's hitting stuff, right? Yeah, it's hitting stuff. And if we think about what the optical depth and how to construct the optical depth physically, I want to now come up with a physical definition or mathematical definition of optical depth. What must it be proportional to? Yeah. N sigma. What's x? Yeah. Yeah. So why don't I call this distance? So this is sort of an overall sense of what tau is, right? Sigma is what units? Yeah, it's like an area. It's units of m squared. This n is what? Number density. That's m to the minus 3. And this distance is just the total distance through that cloud. So if I increase the density of the thing that's, or the stuff that's interacting with the light, then my optical depth goes up. If I increase the cross-sectional area for the light to interact with that stuff, then the optical depth will go up. And if I increase the length over which the light is traveling through this cloud, that optical depth is going to wind up going up. In practice, what you wind up doing is subscripting this thing with a lambda. And if you think about the number density of absorbers as being some sort of fixed quantity in some volume, what's really interesting is understanding what the cross-sectional area is as a function of lambda. So for your notes, this is the distance through the cloud. We can write this in integral form as just being the integral from 0 to s, where if we think about this cloud as some sort of path length through this of size s, here's my star again, and I'm passing through here, of the number density of absorbers at every location along this path times this sigma lambda times ds. Right? So it's the overall amount, if we have a constant density, is going to be this. But if we don't have a constant density, we have to understand what the different density profile gives us for our tau lambda. This is sometimes referred to, if we take out this sigma lambda times n. Just do it with an n without a subscript for a moment. N, sometimes called the column density. And it has units of meters to the minus 2. Right. Okay, so it should be clear that if I increase my distance through this cloud, then I get more extinction. What I want to show you now is sort of an interesting historical plot, actually a reproduction of a historical plot, where people were trying to understand the effects of dust. In fact, they didn't even understand that dust existed and was important in observational terms. In the 1930s, trying to understand the sort of location of the solar system within the galaxy. And what this person named Trumpler did in the 1930s was look at a bunch of open clusters. These are conglomerations of newly forming stars that are fairly blue intrinsically. There's not a large number of them. And he made a plot in these sort of weird units of flux versus the square of the angular diameter of all of these different open open clusters. What's important about this? Well, think about what happens nearby. Well, first of all, he made this assumption that all open clusters were about the same size physically, right? Call it tens of parsecs or something, whatever number that is. Objects which are closer by are going to be bigger on the sky, right, if they're all the same intrinsic size. Objects which are farther away are going to wind up being smaller on the sky. If they're smaller on the sky, well, first of all, let's just try to figure it out. Who wants to help me with this? What's actually, what accounts for this black line here? Yeah, Leah.
What it would be if there wasn't dust, but because of dust, when it gets farther, the flux must be smaller, right?
Yeah, so that's where the inference of dust came from. I want to understand mathematically what that straight line should be. I want to plot flux versus angular diameter squared. Yeah, you're both saying exactly right. I just want, before that one step, I want to understand this black line. Yeah, so F is going like 1 over r squared, but I didn't plot 1 over r squared. What did I plot? Yeah, so he made the assumption that r goes something like theta, inverse theta, excuse me, to the 1. Right? So the farther away something is, the smaller the angular size is. So you wind up assuming that F goes like theta squared, which is reasonable, right? Yeah, so you both said the right thing. What's actually happened is that we've dropped off this line because as you get to large distances or small angular sizes of these open clusters, they're actually fainter and actually turn out to be redder than they would otherwise. If we're thinking about this in terms of magnitudes, right, the magnitudes would be larger than they should for if I extended that line from nearby open clusters downward. Yes?
How accurate is the assumption that they're all about the same size? Is that actually?
It's actually not too bad. It's sort of okay within a factor of a few. But on the scales that this thing is happening, dust is a tremendously important process within the galaxy. And so these are huge diminutions of light. Yes?
I don't understand how r would go as theta, the inverse of theta. Wouldn't the angular size be proportional to how big the radius is?
Oh, sorry. This is distance from us. We've been using d sort of throughout the class, but somebody said 1 over r squared. Yes, you're right. Yeah. So this is r's distance. Okay. So what's really interesting is that this was sort of one of the nice, very clear indications that dust was very important in making measurements within the Milky Way, in particular understanding distances within the Milky Way. So now let's think about the origin of reddening, right? Because if we just have the same size blobs and there's no lambda dependence on these blobs that are causing this extinction, we just have this overall diminution of light. Let's think about reddening now. So this is understanding the wavelength dependence of dust extinction. And there are really 3 regimes of importance. The first regime is where the wavelength of light is much, much smaller than the typical size. So A is something we'll call the typical size of the grain. And you can see from that picture that I showed you of a real dust grain that there isn't one specific size. It's not basically a round blob, right? There's some structure to it. But the overall size there would be a few microns or a few tens of microns. It's the overall size of the grain, if you want to think about it that way. In this regime, you might think of this as the bowling ball regime. The way to think about dust is that they're very, very large molecules, and you have a wavelength of light which is impinging upon it. And all wavelengths of light are blocked the same way. So here's my dust particle. We'll call this size something like A. we have light impinging upon this dust particle, it's going to wind up getting absorbed. There's nothing really special about this wavelength or something which is slightly longer. They're all going to wind up getting absorbed or actually scattered in the same way. So it looks like a brick wall or a bowling ball. And so what we can see right away is sigma grain is going to be something like pi a squared. And that's going to be giving us our wavelength dependence, which is to say that there is no wavelength dependence in this regime. Another regime, regime 2, is where lambda is much larger than A. This is the Rayleigh scattering regime. And now we think about the dust grain as a single speck, and we think of the wavelength of light. Oh, that's high amplitude. These are the distances between the crests. We wind up more or less just scattering instead of absorbing. So here, sigma lambda, complicated physics, goes like some number kappa divided by lambda to the 4th power times lambda g times sigma g. So k is some constant which depends in detail on the shape of the grain. Is there a question? Okay. And then there's sort of the intermediary regime where lambda goes something like A. So the wavelength of light is actually comparable to the wavelength of the size of the grain. This is called the me theory regime, or my theory regime. And here it's sort of in between this very strong lambda dependence, and there's no lambda dependence here. Sigma lambda goes like some other constant, kappa prime, times the overall size of the grain, sigma g, divided by lambda. Both of these have an inverse lambda dependence. So this says that the cross-section for scattering goes down very strongly as I wind up increasing the wavelength, which is another way of saying that if I have some incoming white light, the bluer light is going to wind up seeing a larger cross-section than the red light. So the bluer light is going to wind up being scattered more strongly. And the same thing happens here. This is the theory that's important, and being able to do this sort of from initial calculations and getting this kappa prime is one of the more difficult problems that we have. But this is dependence that's been shown experimentally, and then in theory as well. This is what you wind up getting. But getting this exact kappa value depends on the grains. But this is the regime that matters for interstellar light. So you can see here, blue light sees a larger cross-section. One of the things that's interesting is that because now we have a prescription for coming up with the optical depth as a function of lambda and in any of these different scattering regimes, we can now turn that around and make a plot of what A is. Remember, we said that A lambda is just going to be proportional to tau lambda, right, which is going to be now proportional to sigma g. And we can do that. First of all, let me show you some observations. This is a set of spectra, actually 2 spectra, of stars that have more or less identical identical narrow absorption lines. And we think, because you can actually look at the fingerprints of these different absorption lines, you can compare them to stars within our own galaxy that haven't been strongly affected by dust. We think that we can use that to tell us what the spectral type is. So in particular, these are supposed to be A stars. And these are both A stars in the Large Magellanic Cloud, which is a satellite of the Milky Way. One of these A stars has this spectrum, and the other A star has this spectrum. Now, assuming we haven't made a mistake and these are indeed exactly the same spectral type, they should also have the same exact temperature. But clearly something is wrong here, right? Clearly there's extinction going on. Towards the line of sight of this guy, there's more dust than there is towards the line of sight of this guy. It's plotted in these very funny units. This is how spectroscopists sometimes wind up plotting things, in units of inverse microns, which means that as I go this way here, am I increasing or decreasing in frequency? Let's try that again. What's that? Well, so if I go this way, let's do it this way. If I go this way, which way am I increasing? Frequency goes like 1 over lambda. So if I'm increasing this number, I'm increasing frequency. So I'm going towards the blue this way and towards the red this way. Okay? All right. So what are some things we notice? If indeed these are supposed to have, in the absence of dust, they're supposed to have exactly the same spectrum because they're at about the same distance. Look at the distance between that over there and that over here and compare that to the distance between here. Right? Blue light was much more preferentially extinguished, and red light was less preferentially extinguished. Okay? So that gives us this overall curvature from something which was very blue. We've made it more red. So we've gone from a spectrum like this to a spectrum like this. Yeah? Aha. This gets back to an earlier question. Why do you think there is a dip here? It's dust. It's a property of dust. It's basically telling us that at these wave bands, there's some sort of large feature that's probably common to a large amount of that dust that gives us this preferential extinction along this line of sight. You can sort of make out that a little of that stuff is there. That's actually an important feature, and we don't understand the physics of that feature right now. Yeah?
When we observe distant galaxies, how can we tell which is the greater effect of Doppler redshift versus dust redshift?
Well, the short answer is that a Doppler redshift would take that spectrum and move that little line this way. So you can very easily distinguish those two. It's actually quite hard to figure out exactly the amount of dust because you have to know what it is that you should be seeing and then compare that to what it is that you measure. This is a really nice, I think, clean example of taking a spectrum of two different stars at about the same distance to us, and notice that one has a lot more dust in front of it. And that you see really the two effects of dust there. I'll just do it on this side over here. So if I now plot this value of A lambda versus wavelength, and this is a plot that's more or less in your book, I'll just sort of repeat it here. We have a bunch of different curves that we might wind up drawing. Just to give some context here, this is about 5,000 angstroms. We'll go up to large 10 microns, down to 0.1 microns. This feature here is that feature there. And it's a larger A lambda at this place right here because this just happens to be a fairly broad feature in this space here. This is called the 2175 angstrom bump. It's not exactly at 2175. It's sort of centered at 2175. But it's actually a fairly broad feature, several hundred angstroms. And this is thought to be due to graphite grains. the way to think about graphite grains, they've actually been able to reproduce this feature in the lab using a bunch of different types of grains that they've actually made in the lab, or you can just produce. This is sort of like smoke from a chimney. That's a typical size of about 200 angstroms. So they don't know that this is the case, and this is sort of an active area of research, is try to understand this origin of this bump. But what's interesting is that if you go to other galaxies, not the Milky Way, but you go to other galaxies, you wind up seeing that this bump doesn't even exist. So in some galaxies, the bump is there, in some galaxies it's not. In some sight lines through the Milky Way, the bump is there. In some sight lines it's not, but for the most part, it's there. It's kind of an interesting thing. So the shape of the extinction curve, as it's called, is sight line dependent. As you can imagine, it's difficult to figure out what the sort of total amount of dust is that we're actually measuring, even though I might be able to measure this extinction very well. Understanding the distribution of those dust grains is something that's quite hard. We can't actually individually measure those. This is due to sort of the whole process. Typically, because dust is considered a trace element in terms of the total mass relative to hydrogen and helium, it's actually fairly convenient to notice that one magnitude of extinction in the visual band usually corresponds to something like a column density of 10 to the 21 neutral hydrogen atoms. This is pretty interesting, right? Because dust is, as we'll wind up seeing next time, is actually just sort of a tracer of where most of the mass in the Milky Way actually resides, in the form of gas clouds in the interstellar medium. And we'll see a direct comparison between dust and different forms of gas. Any questions about that? Yeah.
We said that dust is formed from supernovae explosions.
Yes, sometimes.
So we also said 99% of that is from hydrogen. Does that mean just 1% of the supernova explosion is heavier elements?
Yeah. Yeah. I mean, it depends on which supernova explosion you're talking about. Remember that, so type 1a supernovae are thought to be the explosions of carbon-oxygen white dwarfs or carbon-oxygen neon white dwarfs. But all of the hydrogen that was used to make up this white dwarf, almost all of it, went into making up this heavy elements. A large fraction of it, however, was expelled during the planetary nebula phase of that star in the form of basically ionized hydrogen. So yes, the universe is pretty good at recycling even hydrogen, but for the most part, think of a star as taking in a lot of hydrogen, expelling out a lot of heavy elements. But there's certainly plenty of hydrogen to go around that mixes up with those elements to make up the next generation of stars. I should be clear about the origins of dust. One is in these planetary nebula phases, right? So when you're actually expanding outward, it turns out you get the densities about right and the temperatures about right to make lots of dust. And there you're basically making dust out of the stuff that was made in the star itself and also the stuff that went into making up the cloud that went into making up the star. That's one way. The other way is you can also make it in the outskirts of supernovae. So there's really two ways of forming dust. But the constituents of dust are the ones that are produced and made in stars. But the actual construction of dust, which I haven't really told you about, requires a certain range of densities and temperatures that are only found in a few places. Yes?
So how exactly do you define dust? So it does have to be like a relatively large molecule or multiple molecules?
Yeah, good point. I mean, if you had sort of a methane molecule, that's considered a molecule because it's not big enough. But as soon as you get to sort of, sizes that you could actually see in a microscope, if you had this in your laboratory, at the sort of tens of angstroms level or larger, we're talking about large molecules that we would consider dust. But yes, there's a continuum of all the way down to just individual atoms, to molecules, to very large molecules. Typically, anything that has carbon and silicon in it and is larger than tens of angstroms would be considered dust. And you can imagine right away that there's sort of many different processes that produce these large molecules on different time scales in different places. So that would argue that there is actually a distribution of dust grains in sizes. All right, so just to end, next couple minutes, we don't need it that dark. Here's a dust cloud. Again, it's not because there are no stars in this region, right? This isn't a black hole. There are plenty of stars. There's just a big dust cloud in front of us. This is an actual image. This isn't sort of a depiction. And what you'll see when I post the notes is that as you go farther into this dust cloud, you wind up seeing a bunch of stars, and they appear actually redder. Right? But you get so far in, the optical depth is very large, and you don't even see any of these stars at visible wave bands. This is kind of just a depiction of what I showed you before, I think drawn a little bit better. Here, this light is coming through. It appears redder than it would have been otherwise. The spectrum is reduced greatly in the blue bands relative to the optical bands. And here, if I actually wound up looking off over here, I would see a sort of bluer version of that star, because that's the stuff that gets scattered. So it allows us, this sort of two different important aspects of dust allows us to understand nebulae like the Trifid Nebula. It's fairly complicated. This is sort of a depiction of what we're actually seeing. Here's the observer. We're actually looking at two clouds. One cloud, we're looking basically at a bunch of hot stars. This is called an H2 region. We'll learn about that on Thursday. And it has these very nice colors because this is partially ionized, and you wind up getting fluorescence effects. Behind that is a big dark cloud. There's dust inside of this. There's ionized hydrogen. There's trace elements, etc. The light winds up escaping in all these different directions. There's some light which winds up escaping, and it hits this dust cloud, and that stuff winds up scattering some of the bluer light. So what we're seeing here is actually what's called a reflection nebula, because the light that's leaving from this system here is actually hitting this cloud here, which is getting reflected towards us. Wow. Yeah, dude. This is the blue cloud. So we're seeing the two effects of dust. We're seeing really the two effects of dust if we actually look at these dust lanes right inside here. These are actually dust lanes blocking some of the light behind it. Here's a star-forming region with a lot of dust in it. And what you can see right away, if this appears to be very blue and wispy, there's a very bright star which is off the screen, off to the top. Its light is hitting this dust stuff, and it's reflecting off towards us more blue. Okay, so now you know how to understand these crazy nebulae. What we'll do next time is we'll pick up with the way we make measurements of dust and molecules and gas within the interstellar medium. We'll talk about the different phases of the interstellar medium, and then we'll move on to the structure of the Milky Way. My office hours, 3:30 to 4:30 today.